Bismillah ar-Rahman ar-Rahim. We have integral x from 0 to infinity of log x times the polylogarithm of order 4 of x divided by 1 minus x. Subtract and add zeta of 4. Split into two integrals. The integrand here is log x over 1 minus x times the polylogarithm of order 4 of x minus zeta of 4. Here we have zeta of 4 times integral x from 0 to 1 log x over 1 minus x. This is integral x from 0 to 1 of log x times summation over non-negative integer j of x to the j. Integrating term by term, we get summation j from 0 to infinity, integral from 0 to 1, x to the j log x. Using this general result, the integral we have here is minus 1, gamma of 2, which is 1, divided by j plus 1 to the power 2. This integral is minus zeta of 2, that's minus pi squared over 6. This is multiplied by zeta of 4, which is pi to the power 4 divided by 90. Let's go back to this integral. Write down the series representation of the integrand. This is summation k from 1 to infinity, x to the k over k to the power 4 minus 1 over k to the power 4. The result of this part is here. Then we have integral x from 0 to 1, summation over positive integer k of x to the k minus 1 all over k to the power 4. We also have log x over 1 minus x. We have x to the k minus 1 over 1 minus x. This is minus 1 minus x to the power k over 1 minus x. This is minus summation j from 1 to k, x to the power j minus 1. If we integrate term by term, we get this integral, which is equal to minus 1 over j squared when we employ this result. Now we have a double integral, k from 1 to infinity, j from 1 to k, 1 over k to the power 4 times 1 to the power j squared. This part is minus summation k from 1 to infinity, 1 over k to the power 4 times zeta of 2. So the integral of interest is minus summation k from 1 to infinity, 1 over k to the power 4. Between brackets, we have zeta of 2 minus summation j from 1 to k, 1 over j squared. This difference is equal to 1 over k plus 1 squared, plus 1 over k plus 2 squared, and so on. We can write down this difference as summation over positive integer n of 1 over n plus k squared, multiplied by 3 over 3. 3 over k to the power 4 times n plus k squared is equal to this bracket here. The first part is 4 over k to the power 5, between brackets 1 over n minus 1 over n plus k. When we apply the sum with respect to n to this bracket, we get the kth harmonic number. The double sum is 4 times the sum over positive integer k of each k over k to the power 5. This is an Euler sum. When alpha is 5, we get 7 over 2 zeta of 6 minus 1 half. Alpha is 5, so we have 3 terms from here. Zeta of 2 times zeta of 4 plus zeta of 3 times zeta of 3 plus zeta of 4 times zeta of 2. When we multiply by 4, we get 14 zeta of 6 minus 4 zeta of 2 zeta of 4 minus 2 zeta of 3 squared. When we sum this part, we get minus zeta of 2 times zeta of 4. We have minus 2, integral k from 1 to infinity, n from 1 to infinity, 1 over k cubed, n plus k cubed. We can write this as minus 2 summation k from 1 to infinity, summation n from k plus 1 to infinity, 1 over k cubed, n cubed. This is minus 2 summation k from 1 to infinity, summation n from k plus 1 to infinity, 1 over k cubed, n cubed. Add and subtract zeta of 6. This single sum together with this double sum are the square of 1 over k cubed. If we square the sum k from 1 to infinity of 1 over k cubed, we get summation k from 1 to infinity, summation n from 1 to infinity, 1 over k cubed, n cubed. This is summation k from 1 to infinity, 1 over k to the power 6. We obtain this when the two indices are equal. The remaining terms are when the two indices are distinct. The summand here, it has k cubed and n cubed. We can interchange n and k. The remaining terms can be written as double the summation k from 1 to infinity, summation n greater than k of 1 over k cubed, n cubed. This double sum is zeta of 6 minus the square of zeta of 3. We handle these two together, split into two double sums. If in this double sum we rename n as k and k as n, we get this sum. The difference is equal to 0. Collecting our results, multiplying by minus 1 over 3, we get that integral x from 0 to 1 log x over 1 minus x times the polylogarithm of order 4 of x is the square of zeta of 3 minus 5 pi to the power 6 over 2268. The second integral is integral x from 0 to 1 of the dilogarithm of minus x squared divided by 1 plus x squared. We can make use of this integral representation of the dilogarithm function when the magnitude of z is less than 1. The dilogarithm of z is integral t from 0 to 1 z log t over zt minus 1. Replace z by minus x squared. Interchange the order of operations. The inner integral is with respect to x of x squared divided by 1 plus x squared times 1 plus x squared t. This integrand is 1 over 1 plus x squared t minus 1 over 1 plus x squared, all times 1 over 1 minus t. The antiderivative is the inverse tangent of x square root t divided by square root t minus the inverse tangent of x. Using the limits of integration, we get the inverse tangent of the square root of t divided by the square root of t minus pi over 4, split into two integrals. From the previous integral, we obtained that this is minus zeta of 2. Minus pi over 4 times minus zeta of 2 is pi cubed over 24. In this integral, use the change of variables t equal to u squared. After simplifying, we get 4 times integral u from 0 to 1 log u, the inverse tangent of u, over 1 minus u squared. We focus now on this integral, written here using variable x. Subtract and add pi over 4. Split into two integrals. In one of them we have pi over 4, in the other we have the inverse tangent of x minus pi over 4. This part is minus pi cubed over 32. The antiderivative of 1 over 1 minus x squared is 1/2 log 1 plus x over 1 minus x. Let's do integration by parts. The product of this function of x and that one tends to 0, as x tends to 0 from above and as x tends to 1 from below. When we do integration by parts, we also get minus 1/2 integral x from 0 to 1 log 1 plus x over 1 minus x multiplied by the derivative of this function of x. The derivative of the product is log x over 1 plus x squared plus the inverse tangent of x minus pi over 4 over x. Pi over 4 is the inverse tangent of 1 minus the inverse tangent of x. This is the inverse tangent of 1 minus x over 1 plus x. We split into two integrals. In one of them we have the arctangent function. In the other one we have log x times log 1 minus x over 1 plus x. Downstairs we have 1 plus x squared. This integral was obtained in a previous video. Its value involves pi log 2 Catalan's constant and the imaginary part of the trilogarithm of 1 plus I over 2. To evaluate this integral, use the substitution u equal to 1 minus x over 1 plus x. When x is 0, u is 1. When x is 1, u is 0. X is equal to 1 minus u over 1 plus u. Dx is equal to minus 2 over 1 plus u all squared du. We can use the minus sign to have our integral from 0 to 1. 1 over x is 1 plus u over 1 minus u. This product becomes log u times the inverse tangent of u. Without the minus sign, dx is du over 1 plus u all squared. Simplifying, we get minus integral u from 0 to 1 log u, the inverse tangent of u over 1 minus u squared. This is exactly what we have on the left-hand side. Thus, the left-hand side is 1/2 times this part here. Now that we know this integral, we multiply by 4, add pi cubed over 24 to obtain the result of the integral of interest x from 0 to 1, the dilogarithm of minus x squared over 1 plus x squared.